Oh, no problem, Jacob. Thank you very much. It's great to be here, and great to get the opportunity to teach you all this material, or at the very least, subject you all to this material. The One of the things that we're trying today that's really kind of different is that normally what ends up happening with the order of presentation is that the historical method when people are introduced to these techniques is followed, meaning that the first techniques, which are known as Trotter-Suzuki formulas for simulating quantum dynamics, are usually introduced to people, and then post-Trotter techniques are covered. And so today, we're going to actually be trying the opposite. I'm going to begin with showing you how to use a subset of post-Trotter methods. In particular, I'm going to show you how linear combinations of unitaries works. And if I have time, I'll get on to cubitization. And then Yuan Su, right after this talk, is going to discuss Trotter-Suzuki methods, as well as recent developments that largely he, as well as his collaborators, have made in this space. But the point is that I really do want this to be interactive, and I think it's more important that you all walk away with kind of like the intuition and the key ideas behind this, rather than me going through and hitting you with every single technical point possible. So please, if any of you have any questions, throw it on the chat board, and hopefully Jacob will be kind enough to interrupt me during the middle of it. So then in that case, without further ado, I'll share my screen, and hopefully nothing goes horribly wrong, or there's no geeky webcomics up. Okay, looks like I'm safe with the webcomics. All right, so first thing, before we begin, I just really want to make it clear what the job of Hamiltonian simulation is. So at a high level, the job of the Hamiltonian simulation is really, it's a compilation problem, actually, if anything else. What we have is the Schrodinger equation can be thought in the following form. Let's say we've got a quantum state, and we want to find the quantum state evaluated at some time t. This quantum state can be expressed by as in the following form. If this is the initial quantum state that we begin with, then the quantum state that we have under the quantum dynamics at a time t later is found by multiplying that state by this operator known as the time evolution operator. And this time evolution operator ends up taking the form e to the minus iht, where h, of course, is known as the Hamiltonian. And so again, the Hamiltonian here, if assuming that everything is acting on n qubits, this is a 2 to the n by 2 to the n Hermitian matrix, where again, Hermitian means that it's self-adjoint, so it's equal to its transpose conjugate. So this is a particular matrix, and our goal on the quantum computer for Hamiltonian simulation in general is to compile a sequence of gates, which forms a unitary V, such that for some t greater than 0 and epsilon greater than 0, the norm of v minus e to the minus iht is less than or equal to epsilon. So the basic idea is that what we want to do is we've got our unitary dynamics, which is described by e to the minus iht, and we just really want to break this into a sequence of gates. So if we're to look at this schematically, if we have this being psi of 0 over here, and this is kind of the natural evolution, e to the minus iht, carrying through to a state psi of t. What we actually want to do is we want to consider like a physical world where the time evolution ends up looking like this. And what we want to do is we want to map this over to kind of the world of the quantum computer, where we have a state that this is mapped to begin with, let's call it, this will be psi of 0. And now what we want to do is we want to carry out a sequence of probably discrete gates, depending on your computational model, to end up yielding a final state. And that final state in the quantum computer is equivalent to some state in the physical simulation that's distance epsilon away from the final state that you would end up getting. So that's our goal for this. And this is sort of like the ultimate problem of quantum simulation. Just about every subtask in the field of quantum simulation can be reduced to this problem of simulating quantum dynamics. And in particular, if we wanted to do energy estimation, which is one of the standard problems that you want to do in condensed matter physics or in chemistry, what we're interested in doing is we're interested in finding a state psi such that h psi equals e psi, i.e., we want to find an eigenvalue of the Hamiltonian matrix H. And ideally, for most circumstances, we want this to be the smallest eigenvalue. So that's known as the ground state. So often what people want to know is they want to be able to find the ground state energy for a particular system. And the way that this can be done in practice from it is using a process called phase estimation, which I'm sure most of you have heard about, that ends up taking e to the minus iht, acting on a state psi, and some extra qubits off to the side, and ends up mapping that to a approximation of ht tilde over here, such that ht tilde, the encoding of the phase minus the actual phase, is less than or equal to some delta. And the cost for doing this, assuming that we want a constant probability of failure, is in order 1 over delta. And so this is actually really kind of nice in many ways, because if you recall from some of the earlier tutorials on variational quantum methods, the number of measurements that you end up needing for variational methods ends up going like 1 over delta squared. And on top of that, you never actually end up really guaranteeing that you can get the energy out. All of it ends up depending on how close you can get to the ground state within the family of guesses of psi that you're allowed to prepare. And so phase estimation is sort of like, kind of in the long run, it's sort of the most natural and in some ways the optimal method for us to be able to estimate the ground state energy for a system. So this is kind of what we would do in the long run. And one of the biggest ways that we will tend to approach this is, again, by solving the dynamical simulation problem over here, and then throwing that into phase estimation. So that's the whole task. And so everything about this estimation of the energy boils down to the central problem is emulating e to the minus iht on the quantum computer. Now, you might ask, okay, why am I using the word emulate rather than simulate? The reason why I'm doing it is I think in retrospect, it would have been better if the field had have called it quantum emulation rather than simulation. The reason why is that what's actually happening is that the dynamics that we see in the physical world versus the world of the quantum computer, actually what ends up happening is that this dynamics that you see in the world of the quantum computer is actually logically equivalent to the dynamics that you would see in the physical world. So in some sense, if we're like simulating a molecule, it's almost like what we're doing is we're tricking the quantum computer into behaving like it's a molecule. So it's more like actually kind of like if any of you have, used a Nintendo emulator or something like that. It's very much like that. It's the quantum computer is emulating a molecule or emulating a spin system. something more akin to that. So we're kind of like tricking the physics of the quantum computer to behave like the physics of the system. And so this is actually a big challenge because, as I said before, this matrix H is a 2 to the n by 2 to the n matrix. And if n is like on the order of 100 or bigger, then this matrix is enormous. And there's absolutely no way that you're going to be able to brute force take this matrix and then figure out how to translate this matrix over to a sequence of gates. And so this is what we need Hamiltonian simulation methods for, is to find efficient ways of implicitly compiling this over here into a sequence of like Hadamards and C-naughts and whatever, without actually knowing what the unitary is that we're trying to emulate. So that's the central problem. And so the way that I'm going to approach this is by showing you kind of a larger paradigm for compiling quantum circuits. And this larger paradigm is very kind of, people have been implicitly using this for a really long time, but it's only really kind of been within the last, I would say, a couple of years that the power of this this idea has really been realized. And this idea is known as a block encoding. And so I apologize for this. The way that this tutorial is going to go at this point is it's kind of going to go in a little bit of a roundabout way. I'm going to talk about how you can block encode non-unitary operations and apply them on a quantum computer. And then I'm going to show how we can use this in order to implement e to the minus IHT in kind of an indirect way. So are there any questions? All right, cool. So we've got this notion of a block encoding. So let me just explain it at a high level. Quantum computers, apart from measurement, can
Hey, Nathan.
Yeah.
You got a question just now.
Great.
The question is, why is finding ground states given more importance than finding other eigenstates or eigenvalues?
Yeah, that's a very good question. There's a couple of reasons why. In the context of chemistry, what tends to happen is most stable molecules have a large eigenvalue gap. And on top of that, that eigenvalue gap is often much greater than kT, i.e. room temperature. So for those systems, the thermal state that you end up seeing for the molecule is almost entirely in its ground state. So to a very good approximation, you can understand the behavior of a particular system just by taking a look under those circumstances at the ground state properties. And then once you've got an idea about the ground state, you can compute all sorts of things. In particular, you can end up computing forces on particular molecules, or what you can do is you can find free energy differences, which will allow you to determine how reaction rates are going to go, as well as how phase transitions are going to work more broadly inside quantum systems. So that's one of the big reasons why it's used. However, if you're looking at a system that you know is not going to be in its ground state for one reason or another, then in that case, what you should be doing is you should be looking at the excited states. Now, I should mention that ground states in particular, this another reason why people are so interested in them is, unlike excited states, they're actually relatively easy, or they're easier, I should say, to tackle with classical computers than excited state problems are. And so because people tend to, focus more on problems that they can solve rather than ones that they can't, a lot more emphasis is placed on these sorts of problems that are mainly interested in ground state properties. So that's those are the two biggest reasons why people are most fixated on the ground state problems. Although I personally believe that excited states are likely more interesting for quantum computers, because there's nothing about excited states that's any harder than the ground state when it comes to a quantum computer.
All right, great. And we have one more question. Is the phase estimation method and the 1 over delta cost specific for the ground state, or could this also be applied to the excited state? I guess you kind of touched on this with your last comment.
Yeah. So for the phase estimation, it turns out what happens is you can really view phase estimation as implementing a measurement in the system's energy eigenbasis. So if you have the ground state, well, you'll always get the ground state energy back out of it. If you put in the first excited state, you'll always get the first excited state energy back out of it. If you put in a linear combination of ground and first excited state, then you'll end up getting, with a certain probability, the ground state energy and a certain probability, the first excited state energy. So the algorithm is, the only thing that it cares about is what the precision of the final estimate is, not on what the ordering of the eigenvalues of the input state are. So anyways, let me jump on now to the notion of block encoding. And so the block encoding is a really cool concept. So recall that a quantum computer, essentially, what it is it's a machine for applying unitary matrices. Okay. And the unitary matrices that it can apply are exponentially large, which can give it a lot of power. But the thing is that not all matrices that we're interested in are actually unitary. Sometimes, we really would like to apply a non-unitary matrix on a quantum computer. And so, block encoding, to use clickbait terminology, it's sort of like the one dirty trick that quantum informationalists didn't want you to know about, is a way that you can apply non-unitary matrices with some success probability on a quantum computer. And the idea is really, really simple, actually. Imagine what you want to do is I want to apply this matrix A on a quantum state. So this will, because A isn't necessarily unitary, this will end up mapping that to A psi over the length of A psi if I successfully carry it out. And so the question is, well, how do I operationally do this? Now, the notion of block encoding is the following. What we do is we take a unitary U, and this unitary U is said to block encode this matrix A if we can write it as a block matrix in the following form. Okay, where if we wanted to have this matrix acting on the state psi, what we would do is we would create this block vector of, it's literally 0 over here. And so over here, I should just mention, right, this matrix, this sub-block of the matrix is actually a 2 to the n by 2 to the n matrix. And so what we're doing really is we're just embedding this matrix, this non-unitary matrix that we want to carry out as a part of a much larger unitary matrix. And we're going to do that in order to be able to figure out a way of applying it with, again, some success probability, because this is because it's not unitary, it's not going to be deterministic. And so the place where we're going with this, and the success probability we'll see is actually going to be dependent upon this constant alpha that appears in the encoding. So where we're going to be going with this, with Hamiltonian simulation, is what we're going to want to do is we're going to want to build a matrix that's of the form e to the minus iht and question marks and all the rest of them. And again, the reason why I'm putting question marks in all the rest of these blocks is we actually kind of sort of don't care what ends up happening in all of these other cases. The only thing that we care about is that in this one block, the unitary has the correct action.
Hey, Nathan, you got a question.
Yeah.
Can the non-unitary nature of noisy quantum computers be used instead of block encoding?
Yes, it can, but one of the big problems is that, for example, you could use this in order to be able to try to prepare a thermal state, right? Which is one of the things that got people really excited about, looking at models like the Boltzmann machine on a D-wave system, because the Boltzmann machine ends up requiring you to build neural networks by preparing thermal states. But the problem is that you can't. It's very difficult to error correct, and it's very difficult to precisely tune your system, especially in a stable way. And so the nice thing about doing it this way is that if we do it this way, when we can apply all of the formalism of quantum error correction to allow us to apply these non-unitary gates with an arbitrarily small error. Whereas if we did it in the way you're suggesting, we could definitely do it under some circumstances, but we would fundamentally be limited by whatever our experimental control is. Okay.
Oh,
so
okay. Sorry, you have one more question, which actually is maybe along the lines of what I was thinking about too. So someone asked, could you explain how when A is seen as embedded in a bigger unitary, it is still indeterministic?
Okay, so you know what? I'm actually going to get to that right away by showing the simplest example of this. But I noticed another QA circle. Is there another question that I can get to?
Someone just asked what alpha is.
Oh, alpha over here, it's a constant. Okay, so in general, because the unitary matrix has eigenvalues 1, right? Let's assume that I had my matrix A is just, I don't know, 10 to the 100 times, let's say, sigma x. So if I have that, right, how the heck am I going to embed this non-unitary matrix inside a larger unitary matrix? Well, I'm not going to be able to do it because its norm is greater than 1. But what I can do is I can embed a over 10 to the 100 equals sigma x inside this block up here. And that's what this alpha is. It's this constant of proportionality that we need in order to be able to ensure that the larger unitary is actually, well, properly a unitary. So ideally, in a perfect world, alpha would be 1. But we'll see in a whole bunch of examples, alpha, well, won't be precisely 1. But we can still live with that. So, all right, let me go on to the simplest case of doing such a block encoding. And let's assume that what we have is we have 2 unitaries. We've got a U0 and U1. And what we want to implement is A is equal to U0 plus U1. All right. So how the heck am I going to do this? Well, here's the following circuit for doing it. What we do is I'm going to enlarge my Hilbert space by adding only 1 extra qubit in this case. And I'm going to apply a Hadamard down here and do the following sequence of controlled unitary operations. Okay. Now you might, for those of you who've done a little bit of quantum computing, this might look familiar to you. It might look like, the iterative phase estimation circuit, the Hadamard test circuit. There's many circuits that end up following this exact same form. These can actually all be seen as examples of block encodings. But in any case, let's assume that we've got a state psi that we put in. And what we ideally want to do is we want to end up mapping psi to U1 plus U0 psi over alpha for some value of alpha. And we'll compute what the value of alpha will be in this case. So let's go through and do it. So first thing we have is we have the state 0 psi. We're applying a Hadamard gate to 0. So that ends up mapping to 1 over root 2, 0 psi plus 1 psi. Now this empty circle means 0 controlled. So in the branch where the first qubit is 0, I'm going to apply U naught to psi. And in a branch where the first qubit is 1, I'm going to apply U1 to psi. So after applying these two here, I end up mapping at to 1 over root 2, 0, u0 psi plus 1 u1 psi. Okay. Now all I have to do is I have to Hadamard the two. So if I Hadamard the two, I get 1/2 0 u0 plus u1 psi plus 1 u0 minus u1 psi. Okay, so if we take a look at this, what we're saying over here is that if we were to measure this first qubit and get 0, then we would end up applying psi goes to u0 plus u1 over 2 psi. So in this case, we see that alpha equals 2. Now, this isn't terribly surprising because actually we can see that, if we take a look at the coefficients over here, in order to normalize this matrix and make it length at most 1, we would need to divide this by 2 in the most extreme possible case. And we'll see that there's actually some a method to this madness. And in general, this value of alpha is always going to be equal to the sum of the absolute values of the coefficients. Okay, so this is how we do it. And if you recall, the initial state that we began with is 0, and the final state that we want is 0 over here. So what this means is if we view our initial state in this block language as being psi 0 in the block, then the matrix that we're applying is of the form here, u0 plus u1 over 2. And I haven't worked out what these are, but I have worked out down here that this is u0 minus u1 over 2. Okay, so that is basically what the resulting block encoded matrix, and this over here is the block encoding. And in general, what we would do is we would actually, the language that is used is this is known. We refer to these as an alpha k epsilon block encoding. If the constant is alpha, and if k extra qubits are used, and epsilon is the error. So in this case, the unitary is a 2, 1, 0 block encoding of u0 plus u1. Okay, cool. And we'll see later examples of cases where there's approximation error that also come in. But for this one, there's no technical approximation error that ends up arising. Okay, so cool. We've done this for the simplest possible case of adding 2 unitaries, right? Let's talk about the more general case where we want to add an arbitrary number of unitaries. Now, recall that actually we can build any matrix we feel like by adding unitaries together. The reason why is that Pauli operators are unitary. And Pauli operators end up forming a complete operator basis, meaning that any matrix whatsoever can be formed out of a linear combination of Pauli operators. So that means if we were able to do this trick, not just for 2 elements, but sum together an arbitrary number of unitaries, we could actually build any matrix we want with that. So Jacob, is there a question?
There is another question, which I think is related to the first one. It's asking about what the parameter is for the probability we get for applying the unitary we want.
Great. So let's just...
I assume you'll get to that pretty soon.
Yeah, so the probability ends up depending on a couple of things, right? We can see in this case up here, right, the probability that we would end up getting for this guy is really actually just going to be this component squared. So it's going to be like 1/2 psi, or 1/4 plus u1 dagger times u naught plus u1 psi. Okay, now the catch is here that what ends up happening is you might look at this and say, hey, wait a sec, isn't this dagger times the sum of unitaries just always going to be 1? But the sum of unitaries, again, isn't a unitary matrix. You can make anything by a sum of unitaries. So although this is Hermitian, it's not actually unitary. And so the success probability in general is going to end up depending on psi and u0 and u1. Like you can see as a particular example, if I let u0 equal identity and u1 equal poly z, then u0 plus u1 over 2 is actually just the projector onto 0. So by doing this block encoding in that particular form, we can actually implement a measurement. And that's about as, that'll have as strong of a state-dependent probability as you can get. So then, but with a case that is interesting is that with a alpha k epsilon block encoding, using this approach, the probability of success if A is the block encoded matrix is unitary. So if we're trying to build a unitary matrix out of it, then these two terms cancel that we end up getting in this over here. And the success probability only ends up depending on the square of the constant alpha. So the success probability, if A is unitary, is just 1 over alpha squared. So fortunately for the case that we're taking a look at for quantum simulation, when we try to block encode the time evolution operator, the success probability only depends to a good approximation on the value of alpha. But if we wanted to do a generic matrix that isn't unitary, then the success probability is going to depend on our choice of the initial state and our specific choice of these operators.
Okay, Nathan. So you have another question, but do you want to answer it now or keep going? It's about okay, it's cool. Yeah, so someone was curious about, so you talked about this Pauli basis for any operator, essentially. Does this notion generalize to qubits instead of qubits?
So when you're dealing with qubits, right, then no, it doesn't directly go forward. For qtrits, for example, there's other operator bases that don't quite have the same sort of nice properties of being both unitary and Hermitian that you get with polys. But you can look up things like the Gelman matrices in that case that do have those nice properties. But I don't know of, for higher dimensions, any other set of any other operator basis that's as cute as the Pauli basis is.
Okay, so we have one more question. Is block encoding similar to basis encoding?
It's a little bit different in a way, because I mean, if I'm understanding with what you mean by basis encoding, right? It's just by, picking a particular basis to represent the problem. But with block encoding, what the whole idea is to kind of represent your problem in a higher dimensional space. So that way, you can apply non-unitary operations using unitary operations on the bigger space. And it's really just a trick in order to be able to squeeze more out of our quantum devices, which can only naturally do unitary operations, with the exception of measurement, of course. Okay, cool. So let me talk now about the general case, where what we want to do is we want to add a bunch of stuff together. So let's take the case where A is equal to the sum over J alpha sub j, u sub j over here, such that alpha sub j is greater than or equal to 0, and uj is unitary. Now, without loss of generality, I can assume the alpha sub j's are positive. It turns out to not be necessary. You can do a slightly more complicated trick in order to deal with this, but if you can envision if they were negative or had a phase, I can always absorb that sign or phase into the unitary in question. So without loss of generality, we can assume that's already been done. And so the alpha j's are positive. So, or I should say non-negative. So this is the operator we want to build. So how are we going to do this? Well, this process, it contains two operations, which are often called prepare. And what prepare does is it will take an initial state, 0, and map this to a state, sum over j, square root alpha sub j, divided by square root alpha, and yes, that's no coincidence, it's called alpha, where alpha is just equal to sum over j alpha sub j. Sometimes people refer to this as the one norm of the coefficient vector, but I'm not going to use that language too much here. So let's assume that we know how to apply this prepare operation. The next thing we're going to assume is that we've got a select operation. And what select does is it feeds in to the quantum simulation the information about what the UJs are. Just like prepare feeds into the quantum simulation the idea of, or the definition of what the alphas are. So what select does is it will map j and psi for any j to j uj psi. And our goal here is what we want to do is we want to create a block encoding of A, which is again the sum of these unitary matrices over alpha, and we don't care about all of the rest of these coefficients in the block matrix. Okay, great. So now, how do we do this? Well, the way we're going to do this is the following. We're going to copy the exact same intuition we had for the case of 2, but view this prepare circuit as a generalization of the Hadamard gate that I used previously, and select as the generalization of the controlled unitaries that I was using previously. So the circuit for this looks deceptively simple. This is prepare, select, and prepare dagger. And then we have an arbitrary quantum state psi feeding into the bottom. So this is actually all we need to do in order to create this block encoding. So let's show you why this works. So just like going through the exact same analysis, we start out with 0 psi. First step, we apply the prepare circuit, which ends up mapping this to 1 over square root alpha sum over j square root alpha sub j j psi. Yeah, we've got a question.
Yes, Nathan. Somebody was wondering so does A have to be a sum of unitary matrices to do a block encoding?
A doesn't, technically speaking, for a block encoding, it doesn't necessarily have to be represented as a sum of unitary matrices. However, in practice, using one method or another, almost all Hamiltonian simulations implicitly end up breaking up the either the Hamiltonian or the unitary that we're interested in into a sum of unitaries. So basically, it doesn't necessarily need to be. It's just almost in all cases that I can think of at the moment, it is.
And like you mentioned earlier, in principle, it could be, right?
In principle, it always can be, because you can always take it to be a sum of Pauli operators. And in fact, for most physical models, it actually just directly is a sum of Pauli operators. And physics will tell you what those Pauli operators are. So any case, let me go through I'll take a stab at the rest of this derivation. So now I've done the prepare operation. I need to do the select, which will just be gluing on a u sub j to the psi. Okay, and now I need to unprepare. Now, unfortunately, I've only defined the action of prepare on 0. So if you go back and you try to do this at home, this is the step that you're most likely to get confused on, because of the fact that here I've got a sum of different j's, and I don't know I haven't defined what the action of prepare dagger is. So the best I can do in order to be able to describe this state is, unfortunately, prepare dagger 1 over square root alpha sum over j square root alpha j j uj psi. Okay, but what comes in and saves the day is the fact that we want to have the value of this matrix in the top left corner. So what we don't care about the rest of the space. We only care about the projection onto that block. And the projection onto this block can be described by the projector 0, 0, which corresponds to this block 0, 0 of the block matrix. Tensor identity acting on the psi, because we only want to project onto that block of prepare dagger 1 over square root alpha, so on and so forth. But the action, left action of prepare dagger on 0 is defined. It's just the adjoint of this state here. So we know that our state is actually now going to be this inner product is going to be of the form square root alpha squared sum over k sum over j 0 k square root alpha k alpha j over here, and now we have uj acting on psi, just copying this term down. Okay, but these are constants. So this over here is just square root alpha k alpha j delta kj. And using the properties of Kronecker deltas, we end up getting that this is just 1 over alpha sum over j over here, alpha j uj psi, and 0 out here, which is equal to a over alpha psi. So therefore, this circuit, as claimed, is a alpha question mark 0 block encoding of A. So this shows you how we can build any matrix out of this. The only question is, well, how many ancilla qubits we end up needing. And this can actually kind of, vary to some extent. But if we end up having, say, m terms in here, then the number of extra qubits that we end up needing in order to specify all m unitaries is just going to be like ceiling of log base 2m. So you can see that we don't need very many extra qubits in order to be able to do this. So it's a very efficient technique. All right, and that's
hey Nathan.
Yeah.
So somebody was asking, and you were talking about how many ancillas to use, and they're asking. So for large J, it seems like the prepared states are similar and susceptible to noise. And I think they were proposing multiple ancillas as like a solution to that. But do you have any comments about that?
Yeah. So one of the things is that, if you're worried, first thing is that these techniques are usually going to be most useful for the cases where we're looking at doing this on a fault-tolerant quantum computer. The reason why is because even a logarithmic number of extra qubits is really expensive for the present generation of quantum computers. So really, if we're worried about noise resilience, then likely these aren't the right techniques for you. And I think that the techniques that Yuan is going to be talking about next are probably going to be a much better way in order to be able to handle simulation. However, asymptotically, these types of ideas in some cases can perform better than Trotter, although Trotter methods are optimal for their class of problems, it turns out too. So noise resilience, well, I definitely think it's important. It's not what these algorithms are tuned for in the slightest. Okay, so now I've talked about doing an arbitrary Hamiltonian or an arbitrary matrix A. How can we tune this in order to be able to do Hamiltonian simulation? So back to Hamiltonian simulation. So what I'm going to do is I'm going to propose the absolute stupidest way that we could do a Hamiltonian simulation. Let's say we want to do e to the minus IHT, and we want to put this inside a block of a larger unitary matrix. Okay, well, what we can do in this case is we can actually approximate e to the minus IHT using a Taylor series. So we can write e to the minus IHT is equal to the sum from k equals 0 to some final value, capital K, of negative IHT to the capital K, or to little k, over k factorial is the sum. Now, this thing is actually not a unitary, but it can be made arbitrarily close to a unitary just by increasing k higher and higher in order. So this is the way, what we're going to do in order to build it. Now, let's assume that our Hamiltonian is now of the form sum over j, a sub j, u sub j. And this, for example, these u sub j's could, for example, be Pauli operators. And again, all problems in general can be written this way, but in particular, problems like second quantized chemistry as well as spin models actually have a very concise decomposition in terms of the number of Pauli operators. So only a polynomial number in a number of spins are needed. So this is what we have. And if that's the case, then we can express this sum as identity minus I sum over j, a sub j, uj minus 1 over 2 factorial, sum over jk, a sub j, a sub k, uj, uk, and I guess I'll put a t squared out here because I'm running out of space. Okay, and higher order terms. So you can see now, this is actually a sum of unitaries. So we can implement that using the previous techniques that I mentioned. It turns out when you go through all of the mess for this, what we end up finding is that the value of alpha that we end up getting for this is on the order of e to the alpha t. Okay, so what we can do from that, or I should say it's approximately equal to this because we've truncated the sum at capital K. And I'm not going to worry about the truncation error too much. The value of K that we need in order to ensure that our error is epsilon, by the way, it's in order log T over epsilon over log T over epsilon. So it can be made small at, this error can be made small by increasing K at relatively low cost. But the key point is that alpha, unfortunately, ends up growing exponentially with T. So that means if we wanted to use this approach for very large time evolutions, then we're kind of screwed because of the fact that the success probability is going to go down. Oh, I shouldn't say alpha, sorry. What I mean here is I mean A, and A is the sum over J, AJ. So it's kind of like the same idea as alpha. So this is our value of alpha for it. However, if we end up picking t is equal to ln 2 over a, then alpha is equal to 2. And if you recall, our probability of success, if unitary, and this matrix that we're applying is going to be approximately unitary, our probability of success will now be approximately 1 over alpha squared, which is 1/4. It turns out 1/4 is the second best success probability you can ever get in quantum computing. The reason why is because if you have a success probability of 1/4, what you can do is you can use amplitude amplification to boost that up to 100% success probability. And so the way that you do amplitude amplification is basically you need to do 2 steps. One, you need to reflect about the target. And 2, you need to reflect about the initial state that you start with. And so this unitary that you need to do in order to be able to amplify this success probability from 1/4 up to 100% if we end up picking this is just going to be identity minus 2, 0, 0, tensor psi, because that's the reflection about the initial state. And then we need to reflect about our target, which is of the form prep select prep dagger 0, 0 tensor identity times prep dagger select dagger prep. So this is our Grover, it's our amplitude amplification operator, which is just like the Grover search operator. And applying this to our block encoded unitary will mean that we will end up applying e to the minus I h ln 2 over a with probability approximately equal to 1. So this gives us a way for a very special time in order to be able to do time to implement the time evolution operator. So this can be actually turned into a generic time evolution using this idea called oblivious amplitude amplification, but I don't have time to go into that in detail, unfortunately. So for the moment, let's just talk about how we would use this in phase estimation. So if we have this acting on some initial state psi, such that h psi is equal to e psi, then this operator that we can do using this technique with 100% success probability is going to end up mapping on 2 over a, acting on psi, will equal e to the negative I e ln 2 over a psi. And so that means that if we apply phase estimation on this whole thing, then what psi will end up getting mapped to is psi and some extra ancillary qubits. It'll end up getting mapped to psi and a bit string that's going to encode e ln 2 over a. So since the cost of doing this within air delta is order 1 over delta, if we want to learn E within air epsilon, then what we need to do is we need to take our delta goes to epsilon over A, and therefore the cost of doing this is in order A over epsilon. up to logarithmic factors. And I should say also, assuming that you have want constant success probability of, say, I don't know, 2/3. So that is how the cost ends up scaling. It goes like this constant A, which is the sum of the Hamiltonian coefficients, divided by the error tolerance that you want to hit. And it turns out that up to logarithmic factors, this is optimal. Okay, so that is how you can use this technique in order to be able to easily solve problems in Hamiltonian simulation. Now, I'm not going to actually, unfortunately, have the time to prove this, but let me talk about an alternate way that you can use these operations. So cubitization is an alternate way that you can use extra qubits in order to be able to do something very similar to this tactic that I spelled out above. And the basic idea is that with cubitization, what you have is you have a walk operator that is of the form. Now, it's a reflection about the initial state. So you have a okay, you've got a select operation that you're carrying out here. And then what we have is we've got a reflection. Prep 0. Okay, it turns out that with cubitization, what this ends up doing is it ends up essentially creating a block encoding that looks very similar to it, but it will end up creating a block encoding that's of the form e to the plus minus I arc sine of the Hamiltonian over A. And the cool thing about this approach is, and this is question mark. Cool thing about this approach is that the error that you end up getting in this approximation is 0. So unlike the previous approach that I was talking about, where you truncate the Taylor series, this approach over here has no error. And then what you can do is you can just use phase estimation on this guy in order to be able to learn the eigenvalue E in exactly the same fashion that we did above, except now you've got to use the sign to undo the phase. The very last thing that I want to talk about is I want to talk about eigenvalue transformations. So final thing that you can do with this is you can do eigenvalue transformations. And the way that you can do this, and I'll forget the formula, but the way that you can do eigenvalue transformations using linear combinations of unitaries in a cool way is through this formula known as the Jacobi-Unger expansion. So the basic idea behind the Jacobi-Unger expansion here is that what it does is it ends up giving you a way of expressing an exponential of a sign as a sum of unitaries. And so then if we wanted to undo this arc sign of through cubitization and turn it into just the Hamiltonian, then we can use LCU in this particular form in order to undo that. We can also do any kind of polynomial transformation within actually a pretty broad class by applying this trick and using a Fourier series for the function. So these are the central tools. And again, I wish I had more time to cover these last two things, but I just wanted to let you know that they're there, and that this trick of linear combinations of unitaries can also be used to end up implementing non-trivial functions of the Hamiltonian. In this case, this is kind of like the sign of the Hamiltonian that you're applying. And in general, if you had some function like, x cubed, you can end up writing x cubed as like, sine x plus some other terms in a Fourier expansion. And so this trick allows you to be able to do that. So high level, what have we talked about? High level, what I've shown you is I've shown you how you can end up using these block encoding techniques in order to be able to build unitary matrices as subblocks of a higher dimensional matrix. Relative to Trotter formulas, which Yuan is going to be talking about shortly, they end up having the best scaling with respect to the evolution time and the error tolerance out of any known methods. In fact, they're asymptotically optimal, in particular cubitization. But the problem is that they're very difficult in order to use these approaches in order to be able to take advantage of physical properties, such as commutation, or in the case of cubitization, even like the time dependence of the Hamiltonian is very difficult to be able to model. And so other techniques that are more direct for doing dynamics, like Trotter-Suzuki approximations, give you a very, very nice way of exploiting some of these features. But if you don't have features with which to exploit, the kind of sledgehammer approaches that I've shown you here, which have only been developed in the last couple of years, are the best known methods to be able to tackle problems. So thank you very much.